Where do I hit? What's this? Okay. Dave McKay died a while back, and when he did, it really hurt me because it made me realize how much knowledge he had that he never passed on. And I started to think more and more about it. As a university professor, I'm also PO'd at Google because Google gives you the most recent reference, and the kids don't see the stuff that comes from the past. So what I'm going to do today is I'm going to go through and I'm going to give you a random walk through a bunch of topics and emphasize the need for corporate memory, some of the things that have happened in the past that we've forgotten about. Now, these rock boxes, which people have heard me holler about for years, each rock box was a huge piece of aluminum, one solid piece of aluminum from Alcoa down the road from where we are, and it was machined out to make this box. It cost $1 million. And they were very proud of it there because they did all sorts of neat things. They had a little indium foil, knife edge foil there for sealing it. But the fact is that none of them maintained their complete vacuum on the moon, the 10 to the minus 9 tour, or 10 to the minus 12 tour rather. And therefore, we don't have any samples, any lunar samples that are really pristine. Another thing is that we forgot is that the soils that we have now, for example, 10084, were not specifically picked up as soils. The soil here was in place of popcorn. The rocks were thrown in here, and the soil is to keep them from rattling around. So, nobody really cared about soil in those days. It was get the rocks, get the rocks. But the fact is, the soils that we're using are the stuff that was packaged in here. Some of them were specifically taken as soils, but not as many as we'd like to believe. Just a few highlights of things that Dave McKay has pointed out for years, and Dave Carrier particularly in Chapter 9 of the Lunar Source Book, and that is the actual strengths, the mechanical properties of the lunar soil are something that we can't comprehend. The fact that we can have a vertical cut that's 10 feet straight up and down. Now, we can't do that on Earth, okay? That's a property that the lunar soil has that's rather unique. And here's a picture of Dave back in '71. And in order to make a lunar soil that duplicated the properties, we didn't go about using JSC1 or anything like that. We used kaolinite and League City sand right around JSC and put those together and got the proper properties. And then Dave went about great pains to pack these all the way down here. And you have to pack every 2 inches or so, you have to pack it. So the fact is that we don't have that tendency to try and duplicate that on Earth. But in fact, in order to get to what we had on the moon, you've got to really be quite careful. And all the drilling things that Chris has done and Honeybee's done have used lunar stimulants, but in fact, in very few cases, if any, have they duplicated the strength of the soil. Shoot. Just as an example of the strength of the soil is Don Burnett, still around, one of the oldies, was going to do a neutron flux experiment, and he was going to drive his long 1 meter inch spike with the neutron source and everything into the ground. And then Dave showed him that, gave him a hammer and says, go ahead and do it. And he couldn't do it. He couldn't drive it in there. And so with Apollo 15, we had a bunch of mess ups with the drill stems, and then Dave figured that out. In Apollo 16, we realized that you could actually take a core out, and the core, the hollow portion of the drill stem would remain, and you could actually put this down. So it was in Apollo 17 that Don finally got around to doing his experiment. He hammered this thing into the lunar soil. It wasn't possible. And duplicating this packing of lunar simulant is commonly not considered. I've seen all sorts of things. It depends upon the lunar soil you have. You can't just take a crushed up basalt and pour it into something and push it down a little bit. That is what we commonly would think we were doing, but the fact is that's not duplicating the situation on the moon. We talked about lunar simulants. In 1971, January 71, Paul Weibland came to the Second Lunar Science Conference with a bunch of Minnesota lunar simulants. He gave it all out. I still have my little keychain home that he handed out. But the fact is, everybody thought, oh, that's really great. He has a lunar simulant. And people started using it for everything. Now, what he had was a ground-up diabase from up in Duluth, Minnesota, and it didn't have any glass in it. So what we did is we poured some of it through a big plasma furnace, 750 kilowatt plasma furnace, and generated glass, ground that up and put it in. So now we had a basalt with some glass in it, and that passed off as a simulant for years. And then we kept getting different size fractions, and Paul wasn't very consistent. So we thought, well, let's generate another one. So we started with JSC1. And JSC1 in 1993 was manufactured specifically to have glass, or something that duplicated agglutinates to some extent, to have this glass in a simulant. And it had about 50% glass. And since then, we've used JSC1. We now have a JSC1A. We have a whole bunch of new simulants that are being made because there's all sorts of SBIRs out there to make simulants. But the fact is that we still insist that there's a problem with making simulants. This is where JSC1 and JSC1A is at just north of Flagstaff. Now, League, in all its wisdom, and CAPTEM, League mainly instructed CAPTEM, to get the ISRU community together and to do a study to figure out exactly what they needed, how much they needed, all that sort of stuff. And they did it, and we reported back to the NASA Advisory Council. I was the chair of this committee. And I worked specifically with Marshall Space Flight Center at the time, and we determined what they wanted to do. But again, we have a problem because we were not working that closely between the scientific lunatics and the engineers. We seem to have a dichotomy there that doesn't go for a good marriage. And so many simulants were needed, and we decided one size does not fit all. Well, that's brilliant, okay? But the fact is we had problems before because we had JSC1 and everybody was using it for everything. It was meant only for one purpose. It was meant to have glass in it so it could simulate some of the properties of the fragmentary nature of the lunar soil for the mechanical properties, geomechanical properties. It was neither an Amare nor a Highland, but yet it was used for whatever people wanted because the bottle said lunar simulant, okay? So we need all different types of lunar simulant. And the problem is that now they are making all sorts of different ones, but I question why they're making it and the quality of what they're making. We're all familiar with this, the agglutinates in lunar soil and what they look like in polish section. And you see all the glass holding together little rock fragments or anything else. This is basically agglutinate, just pieces of stuff held together with shock glass. And we have then the things that we started to notice on top of these. This was Lindsay Keller was finding this stuff back in the early 90s. And since then, Lindsay in 93 and McKay in 97. And then this is one from Sue Wentworth et al., the same crew. And Sarah Noble has recognized this. This is our Milky Way. This is the only iron metal grain that can be seen with the best optical microscope. All this, which is all iron, is all invisible with the best optical microscope. So we see it with TEMs and SEMs, but then we forget. We used to call it single domain iron. It took us 3 years to figure out what was making the lunar soil magnetic. It wasn't magnetite. That's what our terrestrial hats told us, but it wasn't really that. We figured out, hey, it's all this iron that's all over the place. And so we call it single domain iron, and it was between 3 and 33 nanometers, as was determined by the FMR. But then all of a sudden, the word nanophase became a sexy term, okay? And everybody says, oh, it's nanophase iron. And then nanophase iron, people say, oh, it's something that has an NM after it, so it's less than a millimeter, less than a micron rather. And then, I mean, even Hapke has used the word SM, less than a micron iron. So we're losing track of what single domain iron really is. I mean, single domain iron is a particular size range of iron, and there's also other iron size ranges in there, and that's the SM stuff, the stuff that goes up to 1 micron, and they have two different effects on the spectral reflectance images. Now, this is one that Orbitech was making. Orbitech took some JSC1 and they did some reduction on it and produced nanophase iron. And they made little round balls of glass and stuff like that. But when you look closely at it, everything in there, all these little things are magnetite. There's tons of magnetite in the glass of JSC1, enough to give it all the magnetic properties you ever want. It doesn't need any nanophase iron. It gives it the magnetic properties to use in microwave ovens as well. So the fact is that we spent $1 million making something that I'm not sure does anything. All the white specks are nanophase, titanium magnetite, and that explains all the JSC1 and JSC1A with the nanophase iron don't differ significantly as far as their magnetic and dielectric properties go, which is what they were after originally. Working with engineers, Dave and I can tell you, or Dave could tell you, that it's been difficult over the years, trying to convince an engineer that if I take a soil and I smash it with a hammer and smash it and smash it and smash it and smash it, that the more mature, the more I smash it, the more I'm going to separate minerals. They don't understand, and we didn't understand when we went there, the fact that when you smash up the lunar soil, you start with 100% rock and no minerals, and you start to generate the minerals, and you decrease the rock fragments. And lo, that's just exactly what we thought. But the fact is, there's a crossover point, because what's happening? We're melting things together into agglutinates. So the fact is, the amount of freestanding minerals decreases. So the fact is that we tried to say, okay, the best soil for recovery is an immature, high magnesium sweet, or high titanium mare soil. And we said that back in '92, and people were having problems with that. But when you look at it, gee, it's only too logical. But again, we have a problem with talking between these two groups, scientists and engineers. We did magnetic susceptibility on different soils, different size fractions of different soils. This is low susceptibility, this is high susceptibility, low and high, different size fractions, all the way down to 20 microns. And the point I want you to notice here is things that are labeled plage and pyroxene and ilmenite to some extent. They're nowhere near the end of the, which is agglutinates. Agglutinates is all this nanophase iron stuff that's in there. That's what's there. Plagioclase and pyroxene aren't much different. They have very, very low magnetic susceptibility. Nothing like plage and pyroxene do on Earth. Okay? We have another one. This is a different soil maturity. It's about twice the maturity of the last one. You see the number over here, instead of being 280, is now 610. And so we have a much higher influence of the nanophase iron. But again, the same thing you notice is that pigeonite, pyroxene, ilmenite, not a whole world of difference. Ilmenite on Earth is loaded with magnetite. You can pick it up with a magnet. There's no problem. It's hard to do beneficiation on anything but lunar. We've done the magnetic susceptibility. We've done all sorts of things. And we've done it also on lunar rocks. And it's much, much, much different than anything we could do with any simulant. So what I'm saying in summary, after all my griping and reviewing the past, is that the rock boxes all leak to various extents. We saw rust in them. The question is, where did the rust come from? I claim it comes from the oxyhydration from Houston air. Even the nitrogen, we had all these things under dry nitrogen. Dry? In the mid-'70s, we finally said, hey, let's do an analysis on this dry nitrogen, because it was boil-off from all the nitrogen tanks. It had 25 ppm water in it. Oh, my God. That means everything that had seen dry nitrogen before the mid-'70s had the wrong stuff in it. Compaction lunar simulants is not like the in situ lunar soil at all. Most simulants are not adequate for ISRU studies. It depends upon what you want to do, but most people are trying to do it to either make oxygen or to do magnetic separation, ISRU, beneficiation of the stuff. And so they put all these minerals together and they make a simulant, and it's nothing compared. And I've been at Kennedy, I've gone to these places and showed them that, hey, lunar soil is a world difference than anything you put together as a simulant for beneficiation. And we've got all this single domain iron in it, and it's not really adequate what they've made. But the fact is, why did we make it? We had a big meeting of all the engineers, and I said to them, why are you making this nanophase iron? I don't know, you're the one who said it was important. No, I did, but why are you making it? Well, for magnetic properties, for whatever. I said, yeah, but you're not duplicating. You're using the wrong things. So, we really got to get together between the engineers and the scientists. Lunar minerals not similar to those on Earth. We have iron 3+ on Earth all over. A little bit of iron 3 gives us magnetic susceptibility, gives plagioclase magnetic susceptibility at Earth. That's nothing like on the moon. So you have to worry about all these simulants that we're going to use. And the final thing I have to say is, and I was the head of the committee for many years that didn't want to give out lunar samples, but we have to make these soils more accessible for ISRU purposes. There are certain types of analyses that cannot be done with a terrestrial lunar simulant. And that's just a fact of life. And yet, as scientists, we're trying to protect this. And we have a pristinity level. We don't want to do, but the fact is, we've got to start giving it away more. We've got 50, 60% of the samples have not even been touched. So we have lots to give away. And my last thing to say is, from the Bible Belt, this is what some of our Congress people can do. Okay, thank you very much. Questions? Great. Hungry? Oh, what? Yeah, Clive.
Way in the back.
I think in order to get the correct regolith, yes, we can open up the vault, so to speak, but it may be a strategic move to actually get more and make it a an effort to actually go bring regolith back so we can better understand what's going on there.
Yeah, I agree. Back in the 70s, we were saying, what are we saving it for? What are we saving it for? Give it away, give it away. We're going to go back in a couple of years. Sure. Okay. I don't know. The problem is there's soils that are just unknown to the public that are out there. For example, on the back of the lunar rover, remember they broke off the fender and then they fixed the fender and all that sort of stuff? But it was throwing up dust, and it kept throwing up so much fine regolith that they had to get out and clear the battery packs off because they were coming black-bodied and they were warming up, and so they had to clear those up. When Jack's getting back into the lunar module, just finishing up the last day, he said, hey, what do you want me to do with all this stuff on the back end? We said, hey, put it in a bag. Call it beachless. So we put it in a bag, called it beachless. Okay? Until 3 years ago, nobody knew this existed. And then I remembered, oh, shoot. So they found it. And now they have all this soil, which was thrown up on the back of the rover. Well, it has no real integrity as far as provenance goes. But the fact is, it's lunar soil, and there's lots of it. So give it away. What the hell? Thank you.
Okay, thank you.